Okay. This is the second problem that I wanted to try, and this is a problem where you have a body force, and the body force comes because here's a beam which is not supported, but it's spinning about the origin with an angular velocity omega. So if you take a small element of the beam here, which has uh, volume dv, and its position is given by x1, e1, x2, e2, then uh, the centrifugal acceleration is in this direction, and this acceleration, let's say, is a, which means that the force on that body, the centrifugal force on this small element, would be rho times dv is its mass, right, times the acceleration, which is equal to rho times dv omega square r times r cap, where r cap is the unit vector along this direction, which is uh, uh, r by mod of r. Okay, and so mod of r is r, so the r cancels out. So this is the force, centrifugal force on this element. And the body force, remember, is force per unit volume. So you have to get the body force, you have to divide this by the volume. And so this will go away. And the volume and the body force would be given by rho omega square r, which is rho omega square x1 e1 plus x2 e2. That's your r. Okay, so b1 is rho omega square x1, and b2 is rho omega square x2 for this particular problem. So this is your b. Now uh, the difference between this and the previous problem is that in the previous problem you did not have any body forces, so your plane strain and plane stress equations, Airy stress function equations, were both biharmonic, del 4 phi equal to 0. But in this case we will assume something. We'll assume plane stress, let's say. So we will assume that the thickness of this beam in this direction, x3 direction, is small. So this thickness is small, it's just rotating, plane stress conditions apply, and we will use the equation b1 equal to minus del v del x1 and b2 equal to minus del v del x2 in order to now find out this scalar potential v. So to do that, I have b1 and b2, so I plug it in. So del v del x1 will be minus rho naught square x1. Take do the integration. So if you do the integration, then from the first one you get this is rho omega square x1 square by 2 plus a function of 8, a function of x2. You do the second equation, rho omega square x2 square, this is x2, sorry, x2 square and a function of x1. And then comparing these two, you see that uh, this is a reasonable form. This is a reasonable form of v, which is consistent with these two equations. The constants don't matter. Constants don't matter because v does not enter your equations. Del square v does. So the constants in linear terms don't matter. So this is a minimal approximation for the potential, which will give you these body force components, these body force components. So now we can go back to our Airy stress function equations. And if you remember, yeah, it's here. If you remember that for plane stress, this was the Airy stress function equation. So this is del square V, and we will have to calculate del square V for the V that we have found. So that's easy to do. Once you have the V, Once you have this V, you calculate del square V, which comes out to be this one. Plug it into the Airy stress function equation for plane stress. Now you have to take care of whether you are doing plane stress or plane strain, and this is what you will get. Okay, now this is what we will have to solve. Now we will have to find a phi that satisfies this equation given the boundary conditions. What are the boundary conditions? So all of the boundary of the body is del Vt, and on the top, the normal here is 0, 1, and if you carry out the Cauchy relations, you will see that sigma 2 2, sigma 1 2 has to be 0. Here it is 0 minus 1. You will reach the, this is a traction free surface, this is also a traction free surface, so you will reach the sigma 2 2 equal to sigma 1 2 equal to 0. You will reach the same conclusion on the top and the bottom, and that's what we have done. On the top and the bottom, sigma 1 2 and sigma 2 2 both are equal to 0 and x2 equal to plus minus b. Now on the edges, again we can use weak boundary condition. Okay, so on x1 equal to plus minus a, we use the fact that the total force in the x direction is equal to 0. Total force in the x direction is equal to 0. Now you may ask why. Firstly, why I use a weak boundary condition in this case. Secondly, why I use only one weak boundary condition and not 3 as in the previous problem. Well, I can use 3. I can use the fact that sigma force in the y direction is also equal to 0. The moment is also equal to 0. That will give me two more problems, two more equations from which I can solve the constants in my series. So how many boundary conditions I use, how many weak boundary conditions I use depends on how many terms in the series that I want to, that I plan to use. So in this case, I'm going to use a small series so I don't bother to satisfy the other two boundary conditions. So not satisfying the other two boundary conditions may be fatal, may be very risky, because I may come up with a solution which which does not satisfy the boundary conditions on x1 equal to plus minus a, the boundary conditions that I have not taken into account, don't satisfy them, then they don't really qualify as a unique answer to this problem, because a unique answer requires that all differential equations and boundary conditions be satisfied. So it may not be a unique answer. I run the risk of that. But then if I can guess the solution to a reasonable degree, in many cases I will find out that not only am I able to satisfy the boundary condition that I have taken here, I am also often able to satisfy the other boundary conditions which I have not considered on the weak boundaries, that is x1 equal to plus minus a. So in this case, I don't go through the solution step by step. So I take a small series with only 5 terms, and I do this because what I see from here, I see that phi is so if I take differentiation of phi 4 times, I get a constant. So based on that, I take this fourth order polynomial as my minimal guess. Okay, so if I take this minimal guess, I can derive all the 5 coefficients, all the 5 coefficients that I have here, all the 5 coefficients, I can derive them from these 5 boundary conditions that I have. 4 here, 4 on the top and bottom, and 1 at the sides. So from these 5 boundary conditions, I can derive everything And to make sure that the condition at x equal to a and x equal to minus a are both satisfied, I have to take a suitable function. I have to take a suitable function because I know it's symmetric. So I have to take a function which gives me symmetric phi, and that's what I have done. Uh, and this turns out to be a minimal guess. This turns out to be a minimal guess. And after I determine all the coefficients, please try it out again yourself. These would be the stresses. One thing that I forgot to tell you is this centrifugal force. You know that this is rotating about the center. So what is x1 doesn't remain x1 in the rotation, but I am using a centrifugal force, which means that x1, x2 is a coordinate system that is fixed on the beam and is rotating with the beam. Then only you have an outward centrifugal force acting at each point, and then only your body force is like this. So though this is a dynamic problem, this is a problem where the beam is rotating at an angular velocity. I have converted into a static problem, much like I do it for a whirling stone or something that you did in your high school. Um, in much the same way, I have converted into a static problem by using a frame which is rotating with the beam. That's why you have the centrifugal force. Uh, then it becomes like a static problem where at the back of your mind you have to remember that x1, x2 are rotating with the beam. Okay, so please check this answer out. Please check this answer out, this one. I will stop here. In uh, the next week. We will look at problems which are in polar coordinates. Okay, right.